Alrighty, Roo. So we last PowerPoint we talked about a confidence interval for the mean when the population standard deviation is known. We call this a Z interval. So we kind of talked through. We talked about these ideas of margin of errors. We did this kind of crazy example with a bunch of kangaroos sort of jumping around in our front yard. Now, that was a lot of fun, but perhaps not all that useful in sort of a real applied setting. And why not? That is, if you think back to our previous confidence intervals, the formula from the previous slides, what about them was unrealistic, right? So our formula was what? It was x bar, our best guess for the population mean, plus or minus that margin of error. The margin of error formula was that critical value, that z critical value, times sigma over the square root of n. And aha, you're right. You're exactly right. The part of that formula that's unrealistic is that that formula uses a population standard deviation, when in reality we would seldom know what that is, right? And if we did know what it is, we would probably also know what the population mean is, and hence we wouldn't have to do confidence intervals or inference of any kind, right? It's inconsistent, right? Either we know the population mean, in which case we don't need the interval, or we don't know the population mean, in which case we probably would not know the population standard deviation. So what would we do in practice? So say we go through, we order all these kangaroos, they're delivered, they're dropped off at our house, they're sitting there, we're getting ready to plug our numbers into our formula, and we're like, oh man, I don't know what that sigma is, what should I do? Exactly. NBD, no big deal. So we know that just like the sample mean is a best guess for the population mean, we can also compute a sample standard deviation and use that as a best guess for the unknown population standard deviation, right? So we calculate that S, and we use that as a proxy for sigma. We put that in place of sigma, right? We look at the sort of dispersion or variability in our sample, and we use that as a best guess for the dispersion or variability in our population. And so our new formula looks like this, right? And so, right, kind of big picture, it's as easy as just swapping that sigma for the S. But unfortunately, it sort of changes the mathematics a little bit. And so this is a little bit behind the scenes. You'll have to take my word for it a little bit. But we could show that in this situation, our test statistic no longer follows that z distribution. It no longer follows that normal distribution with a mean of 0 and a standard deviation of 1. It instead follows something called a t-distribution. So our critical value, right, that c still refers to critical value, our t sub c, our critical value is not based off a z-distribution anymore, it's based off a t-distribution. Now, a t-distribution, well, I actually think the next slide will tell us a little bit about the t-distribution. So let's go ahead and take a look. A t-distribution, right, it's just the distribution of a t-random variable. The t-random variable, if you were to sort of graph it, looks a lot like the standard normal. That is, it's centered at 0, it's bell-shaped, it's symmetric. It's sort of indistinguishable from a z to the human eye. But there are differences, and the differences are that it has fatter tail. There's more area out in the tail, so there's more area out in the extremities. Now, just like a z-distribution, t-distributions could be a little bit fatter or a little bit skinnier, right? The mean is always 0, but it has sort of different standard deviation. And the name of the factor that controls that standard deviation is referred to as its degrees of freedom, right? Sort of a technical name. Kind of the reasons behind it are a little abstruse, the reasons behind the naming. But for us, just think of it as like just kind of a number that's controlling kind of the overall standard deviation of that t-distribution. So different t-distributions have different degrees of freedom. The t-distribution that we need, this was shown on the previous slide, has degrees of freedom of n minus 1. So the degrees of freedom that we need to calculate our critical value is our sample size n minus 1. So how do we find these critical values? We can use the table in the back of our textbook to find them. So I actually I scanned a copy of this table. It should be posted on D2L. You may actually already have a copy of your textbook, so either go ahead and open your textbook up, kind of go to that back. It's like it's in the appendix A. It's table A2, or go ahead and pause these PowerPoints. Go to D2L, print up that table, so we can do a couple examples together in the next slide. So if you look at the table, you could see that shape of the t-distribution, and as I said, the shape of it looks like a standard normal. And the table gives us percentiles. It says in the top, percentiles of the t-distribution. So remember, we talked about this. We talked about kind of converting confidence to percentiles. We talked about it last PowerPoint. So for that first bullet point, it says we want 95% confidence intervals. Remember, we meditated, we verified, we understood in our hearts why. A 95% confidence interval, the critical value for that corresponds to what? Exactly, to the 97.5th percentile. So we go to the 97.5 column, and now we just go down for the appropriate degrees of freedom. Remember, degrees of freedom are always n minus 1. So our sample size was 22. That means our degrees of freedom are going to be 21. So 97.5, go down to the 21 column, we get 2.080. Next one. So 99% confidence, the critical value for 99% confidence is going to be the 99.5th percentile. So we go over to that 99.5 column. Sample size of 19 means we want to go to what degrees of freedom? You're right. We want to go down to 18 degrees of freedom. So we go down, 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 way downtown. We get 2.898. Oh, sorry, 2.878. My bad. And then I'll leave that last one for you, right? 90% confidence should correspond to a 95% critical value. Go down to 26 and verify you should get 1.706. Right? And so then it's just using the formula like before. Just replace the sigma with the s. The critical value is a little bit different, and you're good to go. So a couple things that I want to wrap up, kind of a couple loose ends, kind of big picture confidence intervals, either the z or the t. So first off, when we say that we're making a 95% confidence interval, when we say, right, something like I'm 95% confident that the true mean kangaroo jumping distance is between, right, 23 and 27 feet, like what do we mean? Well, it's a little bit of an abstract idea, but imagine generating 1,000 different samples. So imagine, right, repeating that kangaroo experiment over and over and over. You order a different 64 kangaroos and a different 64 kangaroos and a different 64 kangaroos, right? And every sample, right, has a different sample mean, and if we're using it, every sample has a different sample standard deviation. So every sample is giving us, right, slightly different confidence intervals. So imagine thousands of samples, each giving us slightly different confidence intervals. When we create a 95% confidence interval, what we're basically saying is that we expect roughly 95% of these confidence intervals to, there's a typo there, to contain the unknown population mean. All right, that's all we're saying. So if we did 1,000 of them, we would expect about 950 to contain the true mean, but we also would expect 50 of them not to. Now, for any one interval, we unfortunately don't know if it's in there or not in there. Now, we do not mistake our ignorance for uncertainty, right? That is, we would not typically say, at least under a frequentist viewpoint, that there's a 95% chance that the mean is between, like, an actual fixed interval. We wouldn't say there's a 95% chance the mean's between, say, 23 and 27. Or we say if we made a bunch of these intervals, 95% of them will contain the mean, 5% of them, unfortunately, will not. So for any one interval, sadly, we don't know whether it does or don't, but since most of the time it does, we feel pretty confident that ours will. Now, one sort of final kind of wrap-up question, and then we'll look at a little bit of SAS code. And that wrap-up question is this. Why not make 100% confidence intervals? It's a good question, right? That, as I said our government makes 95% confidence intervals. But I mean, we're supposed to be the United States of freaking America, right? We're supposed to be like the best country on earth. Like, why, if we're really the best country on earth, if we really want to make America great again, why are we settling for 95%? That is, we pay a lot of tax money. Shouldn't we expect a more return on that? We pay a lot of tax money. Shouldn't we get in return 99%, 99.9%, right? As close to 100% as possible? So why not do that? Well, I'll leave it to you to verify this, but you can see, actually you can see on the t-table. In fact, actually, if you go all the way, you should have that t-table in front of you, hopefully. If you actually go all the way to the bottom where the degrees of freedom are infinity, those are actually the critical values for a z distribution. Kind of cool, right? Because here's like a little side math fact. You could show mathematically that as the degrees of freedom increase, the t distribution converges to the z distribution. So I'll go along that bottom row, but I mean, it's true if you go along any row. As we're going to the right, that's essentially what? That's essentially the critical value as our confidence is increasing. And what do we observe? We observe that as we go to the right, as our confidence increases, the critical values increase. So why not make 100% confidence intervals or 99.9999999% confidence intervals? Because the critical value would be so large that the confidence interval would be so large that it would be sort of useless, right? Sure, we could be 99.9999999% confident about the mean jumping distance of the kangaroos, but we would be making statements like we're 99.9999999% confident that it's between, say, -300 and 500 feet. And we would say, well, thanks for nothing, smartass. Like, I probably knew that without statistics, without taking a sample. That is, if the confidence is so high, the interval becomes so wide that it becomes almost non-informative. And so, historically, conventionally, right, wiser people than us have decided that 95% is kind of that sweet spot. I mean, we do want to be confident, so high confidence is good, but like I say, that confidence comes at a cost. So we want to temper that confidence. So 95% is that sweet spot between high confidence, but not at the same time inflating the size of that interval too much. Now, how can we create these t-intervals in SAS? We can get t-intervals by using the CLM keyword in procmean. So actually, procmeans will give us confidence intervals for a mean. So back to carbohydrates, if we were to use the CLM statement, this is what? This is our cereal data set, remember? So we had the cereal data set in 511. One of the variables was the carbohydrates for each of the cereals. Here I use the CLM statement. So this is basically saying, based off our sample of cereals, we would say that we're 95% confident that the true mean carbohydrates for all cereals is somewhere between that 13.6 and 15.6. Now, if you wanted something other than 95%, in addition to your CLM, you could use the alpha statement. So the alpha is always kind of 1 minus the confidence. So if you wanted 90% confidence intervals, then you would say alpha equals 0.10, and you would get some output that looks like this. So here we would say we're 90% confident that that the true mean carbohydrates for all cereals is somewhere between 13.8 and 15.4. And, right, side observation, just like we kind of just discussed, right, this is what? This is a smaller interval. Smaller confidence gives smaller intervals. Larger confidence gives larger intervals. Confidence comes at a cost.